Okay, so chapter 11, section 11.1 is on conics. Okay, so right circular cone, the collection of points swept out generated by the line G is called a right circular cone. So here is a nice little figure for us. I would say you don't need to have the parts of the cone memorized. But I mean, I guess it is kind of nice to know, like, here are the napes, which is a fairly interesting phrase. We have generators, and the vertex, of course, is coming into play again, as well as the axis, right? Those of you that like to take handwritten notes, definitely go ahead and jot something down. I would at least draw the diagram out. Okay. All right. So conics. Conic stands for conic sections. They are curves that result from the intersection of a right circular cone and a plane. The conics we will study arise when the plane does not contain the vertex. Okay. Circles, when the plane is perpendicular to the axis of the cone and intersects with each generator. Okay, you can see the diagram there. Again, if nothing else, I would draw out the diagrams. Okay. Any questions on that aspect? Okay. All right. And take a look at the ellipses. It's when obviously the plane is tilted slightly so it intersects the generator, but it intersects only one nape of the cone. Okay. Parabolas. When the plane is tilted further so that the plane is one and only one generator and intersects with one and only one nape of the cone. Hyperbolas, when the plane intersects with both napes. All right. Degenerate conics. If the plane contains the vertex, the intersection of the plane and the cone is on a point, a line, or a pair of intersecting lines. These are usually called degenerate conics. Conic sections are used in modeling many different applications. For example, parabolas are used in describing searchlights and telescopes. Ellipses are used to model the orbits of planets and whispering chambers, and hyperbolas are used to locate lightning strikes and model nuclear cooling towers. I don't know about you guys, but I am planning on getting my PhD at Lehigh. So even though this stuff may seem like you're not going to see it again, um, Math is so wild. I know it's a little bit of a tangent, but it is. It's just so wild. There are articles out there that they're just they're very interesting, and you would think they would not be related to math, and they completely are. So I will leave you with that thought, wrapping up on section 11.1. Okay, 11.2, we're going to talk about the parabola. All right. We're going to analyze parabolas with vertex at the origin, analyze parabolas with vertex at HK, and solve applied problems involving the parabola. All right. Okay, definition. A parabola is a collection of all points P in a plane that have the same distance from a fixed point F as they are from a fixed line D. The point F is called the focus of the parabola, and the line D is the directrix. As a result, a parabola is a set of points P for which you have the following. All right, the distances are equal. Right. Pay attention to the figure. The figure shows a parabola in blue, the line through the focus F and perpendicular to the directrix D is called the axis of symmetry of the parabola. The point of the intersection of the parabola when its axis of symmetry is called the vertex. All right, so parabola is clearly something you should recall from algebra, but obviously we're going to be taking it a step further, right? Okay. Let's check out the first objective. Here's your theorem. Equation of a parabola with a vertex at 0, 0. The focus is at a comma 0, and a has to be greater than 0. The equation of the parabola with a vertex of 0, 0, fitting the rest of the requirements, is going to be y squared equals 4ax. Okay. Definitely make sure that you pay attention to your theorems. And I could be wrong, but I don't know if we even cover all of chapter 11. We might together. I don't know if the rest of the sections will cover all of it. I will find you the rest of the information. Okay. So here's example 1. We're finding the equation of a parabola and graphing it. Find the equation of a parabola at a vertex of 0, 0 and a focus at 2, 0, and then graph the equation. So we know that a is equal to 2. It's literally given to us. So then the equation is y squared equals 8x. So how do you think you're going to draw that? What do you think? How would you draw it? Anybody? So my first question to you is this going to look like a regular parabola that you're used to working with?
No, wouldn't it look like a square root function?
Yeah, it's going to look like it's kind of basically on its side. Okay, you're not just going to have the upper portion, you're going to have both portions this time, but it's going to be on its side. Okay? So to graph the parabola, we find the 2 points that determine the lattice rectum by letting x equal to 2. Then, so we're looking at 2, -4, and 2, 4. These help with the graphing of the parabola because they determine the opening. Okay, this line here, these lines here, would not really be there when you draw it. Okay, you would only really have the blue line. Make sense? Okay. So if I gave you the following information, the distance from a vertex 0, 0 to the focus 3, 0 would be what? What would A equal in that case?
Positive 3.
Okay. So if we were to put that into our equation, what's the equation of the parabola going to be?
12x squared. But yeah.
So just 12x, right? Because the squared part is on the y. Okay, so y squared equal to 12x. Okay, then we plug, if we plug 3 in and solve, we're going to end up getting what points? How do we find the lattice rectum there? What would our points be? You can write it out on paper if you need to. Okay, so go ahead.
Wouldn't it be 3 comma 2 times the square root of 3 and then the negative version?
Right, so we're looking at, this is what we're trying to find. We're given, you already told me that A is equal to 3. Because we were given a vertex of 0, 0. And then we were given a focus at 3, 0. Okay, so that gives us the equation y squared equals 4 times 3 times x. So y squared equals 12x. Okay, so then we have to figure out what our lattice rectum is. So we're going to let x equal to 3. Right? So if x equals 3, then y squared is going to equal 12 times 3. So we get y squared equals 36. So then we end up with y equaling plus or minus 6. So we would have the points at 3, 6 and at 3, -6. Okay? So our parabola would look pretty similar to what we have here, except we have a point at 3, -6, so down here, and at 3, +6. And then we would draw it through the same spot, right? Okay, so that's your second example. All right. So now we're told using a graphing utility, so Desmos or your own graphing calculator, we want to graph the parabola y squared equals 12x. Okay, what do you notice you have to do in order to graph it in a graphing calculator, or more than likely also on Desmos? What do you have to do?
Make two equations.
We're going to make two equations. Good job. Okay. Square root of 12x and negative square root of 12x. How did they find it? They solved for y. Okay. All right, so if you're given the equation y squared equals 4x, how would you analyze it? What are some of the things you can tell me about it?
It's a is equal to 1.
Mm-hmm. A is equal to 1. What else? Okay, let's take a look at it. So we have an A of equal to 1. So then that means that our focus will be 1 comma 0. The directrix is the vertical line at x equal to -1, and the 2 points that determine the lattice rectum are obtained using x equal to -1. So you have plus or minus 2. So the points are 1 comma -2 and 1 comma 2. Right? So figure A on the next line is drawn by hand. Figure B is showing it to you using a graphing tool. If they used a graphing tool, how do you think they did it? They would have to what?
Make two different equations.
Right, they'll have to make the two different functions. I would take note of it so you have some examples written down. Okay. All right, this slide's super important, so if you're not paying attention to anything else, I would write this slide down. Equations of parabolas with a vertex of 0, 0 and a focus on an axis of a greater than 0. So check out your focus, your vertexes, they're all the same. Your focuses change. You have a comma 0 or negative a comma 0 versus 0 comma a or 0 comma negative a. Your lines can switch up, your directrix lines, as well as your equations. And then you have the descriptions that follow. And then obviously underneath you have the 4 primary diagrams. Okay. Give you guys a few seconds to take a look at that. Okay. Looking at example 4, analyzing the equation of a parabola. So if we have x squared minus 8y, take a look at that. What are some of the things you can pull out of that analysis?
It has like a coordinate at 0, 2.
So 0, comma, what kind of 2?
A negative 2.
Negative 2. Okay. All right, so then we have a vertex at 0, 0. We're finally looking at an example where we have a negative focus point, so 0, negative 2. Your directrix is different too. Why is that? Why is your directrix a little bit different?
Because it's in the horizontal direction.
Mm-hmm. Very good. All right, so then your parabola is opening down and the axis of symmetry is the y-axis. All right, to obtain the points defining the lattice rectum, we let y equal to negative 2. So you're looking at negative 4 comma negative 2 and 4 comma negative 2. So what do you notice here as opposed to your other two examples? What are you noticing?
That they're basically the same, but they're just changing some positions.
Right. So instead of manipulating the y, we're manipulating the x. Okay. So pretty similar, but a little bit different. Right. You can take a look at the diagrams. You have the hand-drawn approach, and you also have the graphing calculator. Obviously, when you're dealing with a regular parabola, you don't have to do the split. Okay. All right, take a look at number 5. What can you tell me about the analysis shown in number 5? What can you guys tell me? All right, so we have a parabola with a focus at 0, 4 and a directrix. The line is y equal to -4, so we have to graph the function. All right, so the vertex is midway between the focus and the directrix. Since the focus is on the positive y-axis at 0, 4, then we have an equation in the form of x squared equal to 4ay, with a equal to 4. So then we have x squared equal to 16y. All right. So what do you think we have to do there? How are we going to draw this one out? All right. So if we go through and plug things in, we get x squared equal to 64. So we have x equal to plus or minus 8. So you're looking at the points of 8, 4 and negative 8, 4. All right. Any questions on how to draw these? No? All right. So this is saying find the equation of the parabola with the vertex at 0, 0. If its axis of symmetry is the x-axis and its graph contains the point -1/4, 1, find its focus and directrix and then graph this equation. Well, what's the vertex?
Zero, 0.
Okay, so they gave you that part. Then it says the graph contains a point in the second quadrant, so the parabola opens to the left and is in the form y squared equals -4ax. Okay, because the point -1/4 x, -1/4, comma 1 is on the parabola, the coordinates x equal -1/4 and y equal 1 must satisfy the given equation. So if you plug it in, that means we have an a equal to 1. So you're looking at y squared equals -4x. Okay. Finding the equation of a parabola. The focus is at -0, -1, 0, and the directrix is a line equal to x equal to 1. If we let x equal to -1, then we have y squared equal to 4. So we have y equal to plus or minus 2. So the points -1, 2 and -1, -2 determine the lattice rectum. And you have it drawn there. Okay. All right, those were all parabolas with a vertex at 0, 0. Now we're looking at a vertex that is not going to be equal to 0, 0. All right, it's going to be a little bit different. I would suggest writing down this slide. Okay, we have HK as our vertex. Check out what it does to your focus. What's it do to your focus there? So depending upon a couple of things, we can have some differences there. We can have h plus a, comma k, which will change up our directrix to be x equal to h minus a. Then you have your equation and then your description. The next one has h minus a, comma k. And then again, that messes with your directrix. You have x equal to h plus a. Really, you guys are just going to have to play around with some of these. I definitely suggest if you don't take a picture of this slide, then you definitely write this slide down. Okay. All right. So we're going to find an equation of a parabola with a vertex at 1, -2 and a focus at 2, -2 and graph. Okay, so what can you tell me about those 2 points?
They share a y coordinate.
They do. Okay. So since they share the y component, then we're looking at a horizontal line of y equal to -2 as the axis of symmetry. So the distance a from the vertex to the focus is equal to 1. Also, because the focus lies to the right of the vertex, the parabola opens to the right. So take a look at this slide. It's going to help you break down how you write through your equation. Okay. So we were given a vertex of 1, -2 and a equal to 1. So if we plug in, we get y minus -2. So that becomes y plus 2. And then on the right-hand side, we have 4 times 1. Well, that's just 4. And then x minus 1. Okay. So to find the points that define the lattice rectum, we're going to use x equal to 2. So then you're working it out to be 2, 0 and 2 minus 4. Why don't those look as nice as they did before? Why are those a little bit different now? Before they kind of looked like a mirror image, right? Why do they look a little bit different now?
Isn't it because of the middle term in the y component?
Right, it's because our vertex isn't at 0, 0 anymore. So you're not going to have that really nice looking symmetry when you look at just the points by themselves. But when you look at the whole picture, we're still going to have a symmetrical curve, right? Okay. All right, example 7. Using a graphing utility to graph the parabola, vertex not at the origin. All right. And just as a side note, I do want you guys to know that truly, if we were in person, I would not just be reading from slides. I just really don't want to take away the massive amount of time that it would take me to correctly draw these out for you without getting frustrated. All right. Using a graphing utility for the equation y plus the 2 quantity squared equal to 4 quantity x minus 1. So the first thing we're going to do is we're going to solve the equation for y. All right, so we take a square on both sides. We're going to take the square root to get rid of the square. We get y plus 2 equal to the right-hand side, and then we're going to subtract 2 from both sides. Okay? Why do we have to split this? Why is it necessary to split this before we graph?
Because if we just kept it the same, we were only going to be able to see only one part of the graph.
Exactly, because you are much smarter than the program. If you don't plug in the right things, you're only going to get half the picture. Okay? Remember how much smarter you are than the machine. Okay, so we're going to analyze the equation of a parabola given x squared plus 4x minus 4y equal to 0. So if we complete the square using the x, then we end up getting, it breaks down to the quantity of x plus 2 quantity squared equal to 4 quantity y plus 1. All right. So if you notice, the equation is in the form of x minus h squared equal to 4a y minus k. So then we can start pulling things out. Okay. Here we can kind of see it here. So we get h is -2, k is -1, and a is 1. The graph is a parabola with a vertex at -2, -1. It opens up. The focus is a equal to 1 above the vertex. And then the directrix is equal to y equal to -2. And there you have your little drawing. Okay. Let's look at some application-based problems. Okay. Suppose that a mirror is shaped like a paraboloid of revolution, a surface formed by rotating a parabola about its axis of symmetry. If a light or any other emitting source is placed at the focus of the parabola, all the rays emanating from the light reflect off the mirror in lines parallel to the axis of symmetry. The principle is used in the design of searchlights, flashlights, certain automobile headlights, and other devices. I'm sure everyone has seen one of these. What's one place that you've seen one? Don't say cars. Where have you seen one of these at?
Aren't they also in theaters?
Say theaters?
Yeah.
Yes. So if anyone's ever done any kind of musical theater or regular theater that you did in high school, those are used there, okay? All right. Conversely, suppose that rays of light or other signals emit from a distant source so that they are essentially parallel. When these rays strike the surface of a parabolic mirror whose axis of symmetry is parallel to these rays, they are reflected to a single point at the focus. The principle is used in the design of some solar energy devices, satellite dishes, and the mirrors used in some types of telescopes. Okay. All right, so here's our actual problem, a satellite dish. A satellite dish is shaped like a paraboloid of revolution. The signals that emanate from a satellite strike the surface of the dish and are reflected at a single point where the receiver is located. If the dish is 8 feet across at its opening and 3 feet deep at its center, what position should the receiver be placed? That is, where is the focus? Okay, so we have our diagram. What do you guys think you need to do?
Isn't it if we establish the directress at y equals 8 or negative 8?
Yeah, makes sense to me. So, but we're gonna go with y equals 8, right? Okay, on a rectangular coordinate system, draw the parabola used to form the dish so that the vertex of the parabola is at the origin and the focus is on the positive y-axis. Okay. The form of the equation of the parabola is x squared equal to 4ay, since the focus is at 0a. Since 4, 3 is a point on the graph, that gives us 4 squared equal to 4a times 3. So then a is equal to 4 over 3. The receiver should be located 1 1/3 feet, or 1 foot 4 inches, 1 foot, 4 inches from the base of the dish along its axis of symmetry. Okay, so pretty much right there then, I guess. 1 foot and 4 inches. Okay? All right. Any questions on that section? All right. Let's go ahead and see how long section 3 is. What are you talking about? Thank you. All right, so we have 33 slides there. Let's take a quick second, look at some things. Okay, so for some reason, the only section we're skipping is section 5. I will potentially cover section 5. I'll just pull my own resources for it. Let me go ahead and stop the recording.